Look at computing the percent composition of the various elemental components of a given compound or molecule. First of all, the definition is that the percent composition is the fractional component as expressed as a percentage of the molar mass of each atom in a molecular weight, or you take the atomic mass percentage of the molecular weight total from the empirical formula of the compound. So for instance, if we have sodium hydroxide, NaOH, and we want to know the percent by mass of each component in NaOH. First, the total molar mass of NaOH is the sum of the mass of Na, O, and H, and from the periodic table we would find that to be 40.00 gram per mole. Then quite simply, to find the percent mass of each, I will take what fraction of that total molar mass of the molecule is due to the molar mass of each atomic component. So the molar mass of the sodium is 22.99 gram per mole. I'll divide that elemental molar mass into the molecular molar mass and get a fraction multiplied by 100 and find 57.48% of the total mass is due to sodium. Divide the molar mass of the entire molecule into the molar mass of oxygen, multiply by 100 to convert the decimal to percent, and I find 40% of the total mass is due to the oxygen, and the hydrogen 1.08 gram per mole. Divide that by the total molar mass of the compound and find that 5.2% of the total mass of the compound is due to hydrogen. A nice feature of these is that when you sum the fractional or the percent of each elemental composition, you should get 100%. For example, let's look at the percent by mass of all components of manganese 4 cyanide, MnCN4 taken 4 times. Here, when I do so, I first will total up the molar mass of the compound itself, 159.02 gram per mole. Then I will divide that into the molar mass of the manganese and multiply by 100 to convert to decimal, from decimal to percent, and I get 34.55% of the compound is manganese. Now for the carbon, let's be a little careful. There are 4 carbons in the molecule. The molar mass of each carbon is 12.01. The molar mass of 4 carbons is 48.04. So I will divide the total mass of all 4 carbons by the total mass of the molecule and find the percent of carbon in the compound is 30.21%. Then for the nitrogen, each individual nitrogen 14.01 gram per mole. There are 4 of them present. That's a total of 56.04 gram per mole total. Divide that by the total molar mass times 100, and I get 35.24% nitrogen. Notice another thing about these, that the dimensions of the top and bottom cancel. So there's essentially just a number when I find the fraction, but when I take that times 100, the fraction becomes a percent. We can use percent by mass to determine empirical formula of a compound, kind of going in reverse if you like. Let's consider we have a compound that's 36.3% manganese, 21.24% sulfur, and 42.3% oxygen. So how can we find the empirical formula from that? Well, percent means out of 100. So let's just suppose we have 100 grams of the compound. And if we have 100 grams of the compound, then we would have 36.38 grams of manganese in that 100 grams, since that's the percentage. We'd have 21.24 grams of sulfur and 42.38 grams of oxygen. Then all I have to do is find those. Of course, the empirical formula represents the lowest whole number ratio of these materials in the compound. And these masses don't reflect how many manganese, how many sulfur, how many oxygen are present. We can find how many are present by taking these masses of each material and divide by their molar mass to find the moles, because remember, the moles more accurately reflects how many of each we have. So I divide each by their molar masses and find that there's 0.6622 moles of manganese to 4 digits, because that's the precision to which I know each mass. I have 0.6623 moles of sulfur and 2.649 moles of oxygen. Now, technically, I could build an empirical formula from that information. It would be Mn 0.6622, S 0.6623, O 2.649. But remember, the definition of the empirical formula, it is that it is the lowest whole number ratio. So what I have to do is change these moles into whole numbers, and that can be done quite simply. So what I'm going to do is take those moles that I determined on the previous slide and convert them into a whole number ratio, and the simplest way to do that is to divide by the smallest among them. The moles of S was 0.66, the moles of Mn, as a matter of fact, was a little bit different, 0.6622. So I'll divide them all by 0.6622, and that converts, if you like, I'm finding the ratio in proportion of each to 1 mole of Mn. So I divide 0.6622 into each. I find a 1-to-1 ratio of Mn to itself, of course, 1-to-1 ratio of Mn to S. And when I divide 2.649 by 0.6622, I get a 1-to-4 ratio of Mn to O. So in whole numbers then, my empirical formula of this compound was MnSO4, or that would be manganese 2 sulfate. Let's take a look at another example where this time I will have a compound consisting of N and O, 25.94% N, 74.06% O. Notice that's, of course, 100%, so we have the entirety of the compound represented by those two elements, and we want to know its empirical formula. Again, I'm just going to assume if I had 100 grams of it, since percentage means out of 100, that I would then have 25.94 grams of N and 74.06 grams of O. Just like previously, I turn to the periodic table. I will find the molar mass of N and divide my 25.94 grams by that and get a number of moles of N to 4 digits. I will take the mass of O and divide by its molar mass and get a number of moles of O to 4 digits. Now again, really technically, this compound could be written N 1.851, O 1.629, because those are representative of the ratio of N to O. But the empirical formula is stated in terms of the lowest whole number ratio, so we need to convert these to whole numbers. Continuing with that problem, what I will do is take the 1.851 moles of N, the smallest of the two, divide both of these numbers of moles by that smallest value, and of course I'll get a 1 ratio for N, so for every 1 N, I find 2.5 moles of O. So now I'm going to claim that the formula is NO 2.5. Well, guess what? Remember, the empirical formula is supposed to be in whole number ratio. So instead of a 1 to 2.5 ratio of N to O, in terms of whole numbers, I'll just double both of those and make it an 2 to 5 ratio. So the empirical formula of this molecule is N2O5, or dinitrogen pentoxide should be what it is called. So you should be aware of this and be looking out for this in case this comes up when you have to do one of the problems that I happen to assign to us on our next assessment. If you get a weird ratio that looks like it could be moved up or down in such a fashion so that you can make it into whole numbers by multiplying both components by the same integer value, then you should do so probably. Now, if you're doing this experimentally, you would do this over and over and over again to verify that maybe that wasn't supposed to be NO2 or maybe NO3, and it really is N1O2.5, so that this compound was N2O5 in terms of whole numbers. Let's turn now to the symbolic description of chemical or physical change via what we call the chemical equation. Now, we use the term chemical equation much like you would in a mathematical sense, because in many regards, this is a symbolic mathematical equation. Typically, what we do is we have a side of the reaction, which are the things that we put in the pot initially. We typically call those the reactants. We have a side of the chemical equation where we relate the transformation of those reactants into new species. We call that side the products. And typically, we write the things we put in the pot on the left. So the reactants are on the left side of the chemical equation. The products are on the right side of the chemical equation. Now, between them, what we typically do instead of using an equal sign is that we use an arrow indicating that the reactants are being transformed into products. Now, if there are more than one reactant, if there's more than one product, we separate the species on the reactant and product side by a plus sign. So in that regard, it does seem like we're trying to write this out in a mathematical sense, but there is connotation in terms of mathematics to that arrow in regard to it being like an equal sign. What we will find based on the premise of Dalton, and this was, if you recall back at the time when we discussed the ideas of Dalton, we came to the conclusion that really only one of Dalton's premises of his atomic theory was completely correct. He had first said that atoms were indivisible, which we later learned was not true. They could be broken down. He also said that all atoms of the same element were identical. That turned out to be incorrect as well, because there are isotopes of atoms of the same element. He said that when reactions occur in definite proportion, you're always forming the same material, and that turned out to not be true either. It turns out that there are isomers of compounds that have exactly the same chemical makeup, but they are just bonded and connected to one another in different ways, and they would actually have a definite proportion when reacted, yet really be giving different materials. So the first three of Dalton's premises were not exactly correct, but were as good as he could determine at the time. But I will say that his fourth idea was right on, spot on, rock solid. And that was that when you have a change in composition of materials, the material that we call the reactant is made up of building blocks known as atoms. And the atoms in the building blocks, the building block atoms that are used in the reactants are conserved in the chemical reaction. So the reactants are pulled apart, fragmented, and then reconstituted into the products. But none of the atoms that constituted the original reactants is lost during the formation of the products. We call that a balanced chemical equation. Atoms are not created or destroyed during the transformation. They are simply rearranged. So in order to ensure that atoms are not disappearing, we often have to put coefficients into the reaction to balance the reaction so that we have equal numbers of atoms on both sides. For an example, let's consider forming water from elements in their standard state. So water, of course, is H2O. Water is being formed from hydrogen and oxygen, but the standard state of hydrogen is H2 and the standard state of oxygen is O2. So if you're going to use one H2 unit and one O2 unit to build a water molecule, what it seems like you should do is pull apart the H2, pull apart the O2, stick the O with the two H's, throw the other O away. Take another O2, pull it apart, take an H2, pull it apart, stick one O on with the H2s, throw the other O away. That's not the way nature works. There's conservation of the atoms in the reaction. So when an O molecule, O2, molecule comes apart into two O atoms, each of those O atoms reacts with an H2 molecule that comes apart. So what we're getting at is that we need to form two water molecules every time we take apart one O2 molecule. So in order to build those two water molecules, not only do you need the formation of two water molecules, you need two hydrogen molecules in the pot to react with the O2s. Okay, now let's notice then in the balanced chemical equation that we write, the symbolic representation, I'm going to react H2 plus O2 to make H2O. But it's not balanced in that form. I need two O's on the right to match the two O's on the left. I could do so if I just wrote H2 plus O2 gives H2O2. That would balance the atoms. That would preclude me from throwing any away. But that's not, again, what nature is doing in this particular reaction. H2O2 is a material. It's what is known as hydrogen peroxide. That's when you have a single bond between two O's and then they are bonded outward to two H's. That is really not a very stable molecule at all. It breaks down very easily in sunlight. It actually breaks down very easily in the air as well. But in any event, H2O2 is not H2O. So balancing this chemical equation by changing the chemical formula is not the way to do it. If I'm trying to represent and express that I'm forming water, then the product molecule must be water. So in order to get two O's onto the right side of the equation from the two O's that we began with on the left, I put a 2 on the product side, but I put it as a coefficient in front of the water molecule. Now I do have two O's on the left side of the equation, but I have two H2O molecules, which means I have four H's on the right side. Now I could, again on the left, just change my H2 to H4. If I said H4 plus O2 makes 2H2O, that would be a balanced equation, but the reactant that I'm using is not H4. The reactant I'm using is H2. To indicate I need to have four atoms of H to make two H2O molecules, I'm going to get those four atoms of H from two H2 molecules. So I put a coefficient in front of the molecular formula to give me the total number of atoms needed to build the water molecule. Look at another example of balancing a chemical equation. Let's look at what we will later call the synthesis of ammonia from elements in their standard state. That would be N2 gas and H2 gas reacting to form ammonia gas. Now, what I will do in order to balance this equation is first determine if there's equal numbers of atoms of each element on each side. On the left or reactant side, remember the materials I put in the pot are on the left, so I count up my N's in N2, and of course there's 2. Of course there's 2 H's in H2, and I count the atoms on the right. I have an ammonia molecule, 1 N and 3 H's. So of course I can tell that the equation is not balanced. So what we're going to do really is quite simply do a balancing of these equations by inspection. So it's really simply a trial and error process. Now, believe me, chemical equations can get quite complex, and chemists have devised a sequence of different tried and true steps that you can take to balance difficult equations. And as a matter of fact, balancing chemical equations used to be a point of strong emphasis back in the days when I really first started teaching this class, but it has really been devalued to a large extent. So the point is this: the equations we're going to use, that we're going to balance here, are going to be relatively straightforward equations that are not incredibly difficult to balance. And they can be balanced, as I would say, by inspection, using a little bit of trial and error. So when I have my N2 plus H2 gives NH3, I notice that I need two N's on the right to match the two N's on the left. Now I could change the formulas, empirical formula to N2H3, but then I am not forming ammonia. This reaction is forming ammonia, so I do not balance the equation by changing the subscripts, because literally that's changing the material. So in order to get two N's on the right to match the two N's on the left, I put a coefficient in front of NH3, which gives me a total of two N's on the right. But now, by putting that there, it's saying in two ammonia molecules, since each ammonia molecule has three H's, I now have six H's on the right. So I could put and change on my reactant side the reacting molecule to H6. That would complete the balancing. But again, the reacting species I'm using are individual H2 diatomic molecules. So in order to get six H's on the left, I will simply put a coefficient 3 in front of the H2. And I now have two H's on the left, six H's on the left, and I have two N's on the right and six H's on the right. So I have balanced this equation by trial and error. Again, this is as difficult as it's going to get for us, maybe just slightly trickier, but not much more than this. But you should always make sure that you begin with a balanced equation before you decide to use it further in studying chemical processes. Review some classes of various types of chemical reactions. And while we're doing that, we'll get a little practice balancing them as well. The first kind of reaction I want to introduce is what is known as a single replacement reaction, sometimes called single displacement, because essentially one element kicks another out of a chemical compound. So here I'm beginning with copper nitrate. I'm reacting it with elemental zinc, and as a result of that reaction, I'm forming zinc nitrate, and with that, I'm also forming elemental copper. Now you'll notice one other thing I want to say here is I have subscripts on the materials that are indicating the phase that they are taking during the course of the reaction. First, note that the copper nitrate and zinc nitrate have an AQ subscript beside them. What this means is that they are dissolved in water. So I have dissolved solutions of copper nitrate and zinc nitrate. We'll have more to say about the nature of the copper nitrate and the zinc nitrate a little later when we look at some properties of these solutions. So notice I have a little S besides the zinc and the sulfur. This is an indication, of course, that these are solids during the course of the reaction. So I have some dissolved copper nitrate. I put a piece of solid zinc in there, and as a result, I make some dissolved zinc nitrate and get some solid copper out of the reaction. Now, at this juncture, we are not going to concern ourselves with the why of this reaction, meaning how come the zinc, when I put it in there, will kick the copper out of the solution and take its place. And as a matter of fact, it will. And interestingly enough, if I have a solution of zinc nitrate and put a chunk of copper in with it, it will not kick the zinc nitrate out of the solution. It's not active enough to replace the zinc in an aqueous solution of zinc nitrate. However, zinc is active enough to replace copper cations in a solution of copper nitrate. You will delve into the reasons behind why this occurs when you take your 122 class. For now, let's just recognize that this is a single replacement. Notice that I have a zinc replacing a copper as a cation in an ionic compound. So it classifies as a single replacement reaction. Now let's turn to the idea of balancing it. When I look on both sides of the equation, what I would prefer to do in an instance like this is not worry so much about the individual N's and the individual O's. Since nitrate, N and O only appear in nitrate, they don't appear elsewhere. Now, if they did, that would cause complications. But since the N and O only appear in nitrate, I'm just going to keep the nitrate as a group. Remember, I called it a polyatomic anion anyways, and this polyatomic anion is invariant on both sides of the equation. So instead of counting individual N's and individual O's, I'm going to count individual nitrates. So on the left, I have a copper, a zinc, and one nitrate. On the right, however, I have a copper, a zinc, and two nitrates. So I need to get two nitrates on the left to match the two nitrates on the right. Now, what I could do is change the subscripts on the nitrate on the left, but now if I do that, it's no longer nitrate. So what I do is instead I put a coefficient in front, and I have two copper nitrates in the reaction. Now what that does, of course, is it doesn't affect the amount of zinc, but it does affect the amount of copper, so I will need to balance the coppers not by making it a diatomic on the right, but by putting a coefficient of 2 in front of the copper on the right-hand side, so that I have balanced elements on both sides of the equation at the bottom. For other examples of single replacement reactions, in the first, copper 1 carbonate is replaced, the cation in copper 1 carbonate is replaced by calcium, and we see the balanced equation requires a 2 in front of the copper 2 because of the fact that it is a 2 in front of the copper 1 because it was in the 1 oxidation state, whereas calcium is in oxidation state 2. So again, I don't make diatomic copper elemental copper product. I make 2 individual copper atoms. And then the bottom example is balancing iron 3 nitrate reacting with sodium. Again, we're not going to concern ourselves with why the sodium can replace the iron in the iron 3 nitrate. And as a matter of fact, again, if you had sodium nitrate and dropped a piece of iron into it, you would not have a spontaneous reaction where the iron can kick the sodium out. It only works in one direction and one direction only. What we will see as we learn that we say sodium is more active than iron towards being what we call a reducing agent or forcing the iron out of the compound. But for now, we'll worry about that later. We're more concerned with just identifying this as a single replacement reaction and also making sure we can see how to balance the coefficients in it. Turn to what I will call a double replacement reaction. In a double replacement reaction, we have two things trading places with one another. And here I offer the reaction of dissolved silver nitrate and dissolved magnesium sulfate. Okay, so these are compounds in aqueous medium, which means they are in a solution where water is the solvent and they are homogeneously dispersed among the water molecules. When I put them together, what I end up with is now a dissolved solution of magnesium nitrate, and notice I get a solid form of silver sulfate that is formed. Now what we call the solid that comes out, now notice the other three components are dissolved in water. The final component is a solid that we call a precipitate. So this is also what is known as a precipitation reaction, because the formation of the solid silver sulfate, because of its density compared to the liquid medium surrounding it, it's not buoyant in the water, so it begins to rain down out of the solution, much like precipitation of liquid water through the less dense air as it falls to Earth being pulled by gravity. In a precipitation chemical reaction, we have a more dense solid that rains down through the aqueous medium and falls to the bottom in what we call a precipitation reaction. Now again, one more time, right now we're not going to concern ourselves with why this precipitation reaction occurs. Let's just recognize that this is how we would represent it, and let's make sure that we can balance the equation. Now once again, in this case, I'm not going to break nitrate and sulfate down into NOs and S's. I'm going to, since they remain intact on both sides of the equation, I'm going to treat them as a polyatomic ion that is just like any other atom and balance them on both sides of the equation. So at the top on the left, I have one nitrate, one sulfate, one silver, and one magnesium. But on the right, I have two silvers instead of one, and two nitrates instead of one. So I need to get two silvers and nitrates on the left to match the two silvers and nitrates on the right, and that could either be done by altering the chemical formula of the material on the left, which is incorrect, but I do it correctly by putting a coefficient in front of the silver nitrate on the left, creating a balanced chemical equation. Another example of a double replacement, I have manganese 2 bicarbonate reacting with aluminum hydroxide to form manganese 2 hydroxide and aluminum bicarbonate precipitate. So again, I have 3 dissolved species, one which rains down out of the solution as a solid precipitate, and I have a double replacement where the manganese and aluminum are swapping places. Counting up all the elements on both sides, I see that I need to balance the equation with a 3 in front of the manganese bicarbonate compound, and then I count everybody up and I get the appropriate values for all elements. So Dalton will not be rolling over in his grave. In a combination, or sometimes called synthesis reaction, simpler components combine together to make more complex components. Here I show the reaction of solid sulfur with gas phase oxygen to make gas phase sulfur dioxide. Now, this is not hyposulfite. Hyposulfite would be a polyatomic anion. It would have a charge. This is a molecule that is being formed. It's a bent molecule, as a matter of fact, when we talked about its VSEPR structure. And if you'll notice, I really don't even need any balancing coefficients in this case, because the number of atoms is conserved on both sides of the equation without any coefficients. Here's an example of a slightly more complex combination reaction: elemental aluminum and molecular oxygen combining to form Al2O3, and I count everybody up, and I notice I need 2 aluminums on the on the left and right. But before I do that, notice the trickier thing, and it's really not that tricky, but I need a least common multiple of oxygens on the left and the right. I have 2 on the left and 3 on the right. I could put a factor of 1.5 in front of O2, okay? So this equation could be balanced with a 2Al plus 1.5 O2 gives Al2O3. But I don't react oxygen molecules 1.5 at a time. Oxygen molecules are reacted in whole numbers of molecules of oxygen. So what I'm going to do is find the least common multiple of O's on each side. And that would be 6 O's on each side. So by putting a 2 in front of the Al2O3, I get 6 O's on the right. Putting a 3 in front of the O2 means I have a whole number of 3 molecules of oxygen reacting to give me 6 O's on the left. Now, since I put that 2 in front of the Al2O3, I need 4 aluminum atoms to react to form the 2 Al2O3 molecules as a result of the reaction. Remember, I don't make it Al4 subscripted. That is not the elemental form that aluminum is reacting in. Decomposition reaction is, I guess, for lack of a better way to say it, an opposite of a synthesis or combination reaction. We're taking complex materials, breaking them down into simpler materials. So for instance, if I take ammonium carbonate and heat it up a little bit, it will decompose into ammonia gas, water vapor, and carbon dioxide. What I show below there is the trial and error balancing of that equation. I see that I need to have 2 ends on the left and the right, so I put a 2 in front of the ammonia. And when I count everything up, I note that again I have a balanced equation after performing that simple stoichiometric addition of a coefficient of 2 in front of the ammonia. Talk about a class of reactions that are familiar to most of us, or even your mom and them. That would be a combustion reaction. And in combustion, we have reaction with oxygen, because as we talked about earlier, oxygen has this O2 double bond in it that is highly energetic. When you break that double bond in O2, it leads to highly exothermic or energy producing reactions. So for millennia now, humans have used combustion reactions to generate energy and make energy to make our lives work a little more efficiently and a little safer and a little more conveniently. So anything technically that is reacting with oxygen is undergoing combustion, but most familiarly what we do when we do combustion reactions in the generation and harnessing of energy, we often do combustion with hydrocarbon fuels. And let's look then at the very important class of hydrocarbon combustion reactions. If a hydrocarbon, which of course is an organic molecule composed only of carbon and hydrogen, if a hydrocarbon molecule undergoes what we will call complete combustion, under complete combustion, a hydrocarbon molecule forms products of carbon dioxide and water vapor. Those are the only products formed upon the complete combustion. So what I show in the equation below is the complete combustion of gaseous methane, CH4 plus O2 to make carbon dioxide and water vapor. Now then, below that I show the coefficients, the trial and error of the balancing coefficients I need to put into the equation to balance it. I notice I'm going to need to get the right number of O's on the left and the right to pull this off. To do so, I'm first going to balance my H's. I have 4 H's on the left, put a 2 in front of the H2O, gives me 4 H's on the right. And of course, now what that does is it makes a total of 4 O's on the left and right, so that I need, instead of making an O4 as a reactant, I will have 2 O2 molecules reacting with my methane. More importantly, what I see in the complete combustion of methane is I get a 2-to-1 ratio of fuel to, actually oxygen to fuel. So I have plenty of oxygen available for the complete combustion process. When you're lighting your Bunsen burner in lab, this is what you're doing when you're turning the barrel to open the little windows or valves at the bottom of the barrel. You're introducing enough oxygen into the barrel to mix with the methane in the barrel so that you can perform complete combustion and get the pretty blue flame that results, which shows you're forming a product of carbon dioxide instead of the alternative that we'll see on the next slide. So anytime you have complete combustion, I want you to recognize of a hydrocarbon, you will be forming only carbon dioxide and water as products. Now, again, this is safe combustion in the sense that these two products are not going to kill you when they are being formed. Now, what we have learned after 1,000 years now of burning, actually more than 1,000, but really getting serious since the last 1,000 years, burning lots and lots and lots of hydrocarbon fuels. We've been dumping way too much carbon dioxide into our atmosphere. That has turned out to be a problem. But ultimately, if you burn flames in a closed room, the carbon dioxide that you're generating won't be lethal to you. So complete combustion is a safe type of combustion, and it's a preferred type of hydrocarbon combustion. In addition to complete combustion of a hydrocarbon, I want you to be able to recognize two forms of incomplete combustion of hydrocarbons. So there is one complete combustion form. There are two incomplete combustion forms for hydrocarbons. In both cases, the ratio of oxygen to fuel has been lowered. So what we will learn then is the maximum ratio of combination of fuel to oxygen, or really maximum oxygen to fuel ratio, guarantees that you get complete combustion. Lower ratios of oxygen to fuel means you will get incomplete combustions, and they will be of one or two types. So before we move on, let me point out to you that this is why we say that you should burn fuels in a well-ventilated area. Ventilated doesn't mean letting the exhaust gases out as much as ventilating means letting reacting oxygen in. In order to get complete combustion of a hydrocarbon, to maximize the safety of the reaction and get the correct products that are safe to humans, at least initially, and instead of if you dump them for 1,000 years, that's different, but for initial instances, you want to form carbon dioxide because it won't kill you. And if you ventilate the reaction correctly, you put the maximum oxygen to fuel ratio, and you will get the complete combustion. If you don't ventilate the reaction as well, you'll have a lower oxygen to fuel ratio, and you can get either one of these two forms of incomplete combustion. In the first, which again is the same reaction I showed on the previous slide, methane plus O2, but now the products in this first form of incomplete combustion are CO and H2O. They are carbon monoxide and water vapor. Now remember, in complete combustion, I got carbon dioxide and water vapor. Now the problem with this form of incomplete combustion is, like CO2, CO is a gas, and like CO2, CO is clear and colorless, so you can't tell it's being evolved in the process. But unlike CO2, CO is lethal. Carbon monoxide is formed when the reaction is not well ventilated. You burn your hydrocarbon, you can make this gas that will kill you. So when they talk about ventilating your reaction correctly, when you're burning kerosene heaters and things like that, make sure you're getting enough oxygen to it so that it is not forming this particular product. Why is this particular product bad? Well, if you breathe in CO, the hemes in your blood cannot differentiate CO from O2. They tie CO up in the locations that O2 should be tied up in your hemes, and the blood carries it out to your cells. The hemoglobin tries to introduce carbon monoxide into the cells instead of O2. Cells only know how to respire or do metabolic things with O2. So the cell says, I don't know what to do, so I'm just going to die. So you asphyxiate yourself with carbon monoxide poisoning because cells don't know how to process carbon monoxide. They only know how to process O2. Now, when I balance this same equation that I saw on the previous slide, I end up with the coefficients 2CH4 plus 3O2 to form the carbon monoxide and water vapor. Now notice that's a 1.5 to 1 ratio of O2 to fuel. Complete combustion was a 2 to 1 ratio. So by not providing enough oxygen to the reaction, lowering the stoichiometric ratio of the oxygen to fuel, I will get these products formed, which again are lethal. Now in the second form of incomplete combustion, which again, I want you to recognize the reactants are the same, but I'm getting different products. So I want you to know what the reactants are simple. They're fuel, hydrocarbon fuel, and oxygen. The products of complete combustion, the difference is complete combustion forms carbon dioxide. Incomplete combustion either forms carbon monoxide, bad, or carbon. Now carbon bad as well, really, ultimately, carbon, elemental carbon being formed from the combustion, as we see in this final reaction. You still get water vapor, as you do in all three, but elemental carbon is what we would call soot. It's that black grimy stuff that comes out of combustion processes. And also, you can tell you're forming carbon as a product when you see yellow flames. Yellow flames result from highly ionized and excited states of carbon atoms where their electrons are cascading and emitting energy as they fall from excited electronic orbitals back down to their low or ground state electronic orbitals, and they emit the characteristic yellow lights that we see when we burn hydrocarbon fuel flames. So anytime you see yellow flames, you can guarantee you're doing this form of incomplete combustion during that particular process. Notice if I balance this chemical equation, which I have done, I have a 1-to-1 ratio of O2 to CH4. You can do the same thing by closing the barrel on your Bunsen burner, and the flame will turn into a bright yellow because you've decreased the oxygen to methane ratio down to a 1-to-1 ratio, and you're getting elemental carbon being formed as the product, and you're making the yellow flame as a result. So again, I want you to recognize for complete combustion, the carbon product formed is CO2, and for the incomplete combustion, you're forming either CO or C, and these are because of the reduced ratio of oxygen that you're supplying to the fuel. In this slide I show the trial and error balancing of the coefficients for the complete combustion of liquid benzene. Liquid benzene, C6H6, reacting with O2, and in its complete combustion, I form CO2 and H2O. Count everybody up, and I see that actually nothing is in balance on either the reactant or product side. So I will first balance the C's on both sides and the H's on both sides by putting a 6 on the product side in front of the CO2 and a 3 on the product side in front of the H2O. Now when I count everybody up, I have 6 C's on both sides, 6 H's on both sides, but I have on the product side 12 plus 3 or 15 O's, and on the reactant side only 2 O's. So I need to balance the O's on the left and the right to complete the process, but if I put a fraction of O2's on the left, 7.5 times 2 gives me 15 O's on the left and right, but 7.5 is 15 over 2. That's not whole numbers of O2's being reacted. Even though these coefficients in the third equation do balance the reaction, I want whole numbers to balance my equation. So what I'm going to do is change my fraction into a whole number by eliminating its denominator, but to make everybody equivalent and balanced, I have to do the same process to all reactants and products in addition to the O2. So I will multiply the entire equation by 2, and that eliminates the fraction that was balancing the O2 and gives me the least common multiple of balancing coefficients for the complete combustion of liquid benzene to be 2 benzenes plus 15 O2s gives 12 CO2s plus 6 H2Os. Give a fancy name to the relationship between the balancing coefficients that we have placed in front of reacting species and product species in our balanced chemical equation. I'm going to call these coefficients the stoichiometry. So this is a big fancy word, and it's going to be a very important word for us going forward in understanding what we can now do with a balanced chemical equation. So what we see in this particular reaction is liquid benzene, that's C6H6, with the subscript L telling me it's in the liquid phase. I'm actually going to combine it with oxygen in a very familiar process that we'll describe a little more in more detail later, that I would call combustion. And I'm forming carbon dioxide and water as a result of this combustion of methane. Now, you'll notice, combustion of benzene. You'll notice that I have chosen coefficients, the lowest possible whole number coefficients that balance this particular equation. Okay, let's be very clear about that at this juncture. First, let's count and note that I have 2 times 6 or 12 C's on the left, and I have 12 times 1 or 12 C's on the right. I have 2 times 6 or 12 H's on the left, 6 times 2 or 12 H's on the right. I have 15 times 2 or 30 O's on the left. I have 12 times 2, which is 24, plus 6 times 1, which is 6. I have 24 plus 6, or 30 O's on the right. So I have a balanced number of atoms of each constituent building block on the left and right. So this is a balanced chemical equation. So what I'm getting at is that 2 molecules of benzene must react with 15 molecules of O2 to give 12 molecules of CO2 plus 6 molecules of water. But for quantitative purposes, in terms of doing calculations involving how much of each species I should put in the pot and how much of each species I can remove from the pot, I'm going to use the bushel basket of chemistry. And the bushel basket of chemistry says that instead I have 2 moles of benzene liquid reacting with 15 moles of oxygen gas, forming 12 moles of carbon dioxide gas and 6 moles of water in the vapor form. Now, before we move on from this, let's be very explicit and point out that what I want you to do when you balance equations is write them in terms of the lowest whole number balancing coefficients. These are the least common multiples of all values. These are the smallest stoichiometric coefficients, we would call them, that make the atoms satisfy Dalton's requirement of conservation of matter. Now, what I would point out to you, though, is that literally there are an infinite number of coefficients which will properly balance this equation. Meaning, I could have had 4 benzenes plus 30 O2s gives 24 CO2s and 12 H2Os. If you count all the atoms up, I would have exactly the same number of atoms on both sides. I could use 20 benzenes plus 150 O2s gives 120 CO2s and 60 H2Os. They would have conservation of matter on both sides. I could use 2 million C6H6 plus 15 million O2 gives 12 million CO2 plus 6 million H2O, and I would have equal numbers of atoms of each on both sides. The stoichiometric coefficients which you identify should be the lowest whole number values which balance the equation. Let's be clear about that. That's what I expect you to do. How to use stoichiometry to get some quantitative information from a chemical reaction. You see, what Dalton is saying here is I'm happy that we're not creating or destroying atoms. But what we are recognizing now is when I go to put these things together, for every 3 O2 molecules I put in the pot, I had better put 4 ALs in with them. And every time I mix them in that proportion, I can remove 2 product molecules out of the pot. So this will tell me something about the ratio of how many I need to mix together and how much quantification of the product I can expect when I put the proper ratio of reactants into the pot. Now let's suppose that I happen to have on my shelf 3.8 moles, or I'm sorry, but let's suppose I'm making this for profit and I'm selling aluminum oxide to some customer, and the customer calls me and orders 3.8 moles of Al2O3. Now I'm going to get my oxygen out of the air, but I need to put my reactant Al into the machine to make the Al2O3. And of course I want to be conservative, and I want to put just the minimum amount of Al into the machine so that it makes exactly 3.8 moles of Al2O3. What I can do is use the stoichiometry as a conversion factor. According to the balanced equation, every time 2 Al2O3s are formed, I must use 4 aluminum atoms. So I set those balancing stoichiometric coefficients up as a conversion factor in a dimensional analysis problem, converting 3.8 moles of Al2O3 into the number of moles of aluminum. And I do that at the bottom of the slide. Again, this is simply now a dimensional analysis problem where the conversion factor is 4 moles aluminum equal 2 moles of Al2O3. I want to eliminate the moles of Al2O3, so I put the part of the conversion factor containing the Al2O3 on the bottom. That naturally puts the part of the conversion factor for the aluminum on the top. And then when I dimensionally check, the moles of Al2O3 divide out, and my answer is in moles of aluminum, which is what I'm trying to convert to. So this is simply using balancing coefficients or using stoichiometry to perform a unit conversion from moles of aluminum oxide into moles of aluminum. Okay, so now that I see that the dimensions are correct, I know that the numbers are lining up correctly, so I'm told to take 3.8 times 4, divide by 2, and I can convert the moles of aluminum oxide into moles of aluminum by performing that process, and I would need 7.60 moles of aluminum put in the pot to make the 3.8 moles of Al2O3. Another example, this time for the synthesis of ammonia. Suppose I react 30 moles of H2. How many moles of ammonia is it possible to form if I completely react all 30 moles of the H2? Notice from the balancing coefficients, first I begin at the top with a balanced equation. Notice 2 n's on each side, 6 h's on each side. These are the lowest common multiples or minimum stoichiometric coefficients that balance this equation. But according to them, every time I react 3 moles of H2, I form 2 moles of NH3. So I can use this as a conversion factor to change my moles of H2 into moles of NH3. I begin with my 30 moles of H2, and I set up the stoichiometry so that I eliminate the moles of H2 with its stoichiometric coefficient, produce the moles of NH3 by putting its stoichiometric coefficient in the ratio on the top. So that tells me to take 30 times 2, divide 3, or that by reacting 30 moles of H2, I will produce 20 moles of ammonia as a result. Now, the other thing to keep in mind is that these stoichiometric coefficients are exact. Even though I'm using only the integer 2 and the integer 3 in the unit conversion, I'm assuming that the integer 2 is 2.000000 for significance purposes, and that the coefficient 3 is an exact conversion factor. It is 3.000000 as well. The previous slide, I found that I would produce 20 moles of ammonia if I reacted 30 moles of H2. Well, how many moles of N2 do I need to put in the pot? Now, to be honest with you, I could calculate this using the stoichiometry of either H2 to N2 or NH3 to N2. I can do it in either fashion, and I would arrive at the same value for the amount of N2. Let's use the amount of NH3 that I found on the previous slide that would be produced. 20 moles of ammonia being produced, and the stoichiometric connection between ammonia and NH3 is I see that for every 1 mole for every 1 mole of N2 reacted, I will produce 2 moles of NH3. So the stoichiometric connection is 1 to 2 from N2 to NH3. So I will use that as a conversion factor to change my 20 moles of ammonia into moles of N2 by setting up a ratio of those stoichiometric coefficients, eliminating the NH3 and changing into moles of N2. So the NH3 stoichiometric coefficient goes on the bottom, the N2 coefficient goes on the top. Notice I just design my own recipe to do so by lining them up in this fashion. So I note that the moles of ammonia divide out, leaving me only in moles of N2. So everything's lined up correctly. So it tells me I need to take 20 NH3 over a 1 to 2 ratio. 20 times 1 divided by 2 means I would have needed to put 10 moles of N2 in the pot to completely react and form 20 moles of NH3. Now again, I told you earlier that I could have done the same conclusion by the starting material of H2, which I used to find the 20 moles of ammonia. The previous slide says 30 moles of H2 reacted, 20 moles of ammonia were formed, we found. Well, just think of that. If I started with 30 moles H2 and I wanted to convert to N2, the stoichiometric coefficients between N2 and H2 are 3 and 1. So instead of the ratio I show there, I would have used 30 moles H2, 1 mole of N2 for every 3 moles NH3. And when I divided that out, I still would have got 10 moles of N2 react when 30 moles of H2 react. All these things have to hang together because the stoichiometric coefficients are telling me the ratio and proportion of reaction. Another example, this time the formation of iron 4, actually Fe3O4 is what we're forming here. So that's a compound that is not really rust. Rust is Fe2O3, but we're forming another ore of iron that is often mined out of the ground from this particular reaction. Notice we have a balanced chemical reaction for this formation, where I'll have 3 atoms of iron reacting with 2 molecules of O2 to form one Fe3O4 unit. So first, how many moles of Fe are required if I'm going to completely react 0.640 moles of O2? According to the stoichiometry, every time 2 moles of O2 disappear, 3 moles of Fe disappear. So I line up the stoichiometry between those two to get rid of the O2 and form the Fe. So I will line them up as shown, the ratio of 3 to 2. So the numbers tell me to take 0.640 times 3, divide 2, or I will need to react 0.960 mole of Fe. How many moles of the Fe3O4 would I form? Well, I Note there that for every 1 mole of Fe3O4 formed, I react 2 moles of O2. So you should be able to set that ratio up and determine that if I'm going to begin with 0.640 moles of O2, I will form 0.32 moles of Fe3O4. Now, as a matter of fact, if I use the 0.96 moles of Fe and use the stoichiometry between the Fe and the Fe3O4, I would also find that 0.320 moles of Fe3O4 are formed if 0.960 moles of Fe are reacted. It all has to hang together because these are the ratio and proportion of all species. So far we've seen how to use the stoichiometry to convert between one type of reactant into another, or from one type of reactant into how much product will be formed. Well, in practice, that is not the way we do so in these determinations in the laboratory. Why? Because we don't have mole tweezers. We don't scoop up mole shovels full of materials and put them into the reactant pot. We don't scoop out products in moles when the reaction is over. What we do is we go to the scale, we weigh out a certain amount of reactant. From the mass of reactant, we infer how many reactant molecules we put in there. And then when the reaction is complete, we weigh up the amount of product we have formed. And from that weight and knowing the molar mass of the material, we can determine the moles of the product that are formed. But you cannot directly use stoichiometry to relate the weight of reactant to weight of product. The stoichiometric coefficients tell me the number of reactant molecules in relationship to the number of product molecules. The mass just simply tells me how gravity is pulling them to the earth, the kind of force that they will exert on this planet. Now there is, as we have learned, a connection between the mass of a reactant or product and how many are present in that sample of reactant or product. The connection between mass and how many is the molar mass. So what we do when we do laboratory calculations involving stoichiometry is we have to add an additional step onto each end. What I will do to get a certain amount of reactant into a reacting vessel, I will weigh it. But in order to use the stoichiometry to find what amount of product it will form, I must convert that mass into moles. So I have to first do a step where I convert the reactant into moles by using the molar mass. Then I can use the stoichiometry of the equation in step 2 to convert the moles of the reactant into moles of product. Now to compare with what I am doing and what kind of yield my particular experiment is giving me, I'm not going to count out the product molecules that I form, but I'm going to weigh the product molecules that I form. Then I can use the moles of that to convert to the mass using the molar mass of that product. So let's look at some examples of using these steps in the process. I have the following balanced equation for reacting magnesium with oxygen to form magnesium oxide. And I wish to know how many grams of magnesium oxide I will form if I burn 4 grams of O2 in a pile of magnesium. Well, so essentially this is the same as what I was doing before. I have a known reactant and I want to convert it into a known product. But before I had moles of reactant converting to moles of product, which is what I can do connecting them through their stoichiometry, but I cannot directly say that the grams of MgO are connected to the grams of O2 that are reacting. The stoichiometry tells me the number of reacting molecules, so I must first convert my mass of reactant into how many reactant particles I possess in that mass. So my first step is to take the mass of O2, convert it into moles of O2. Now notice this is O2 that I'm converting, so I need the molar mass of O2. It's a common mistake to use the molar mass of O here. I use the molar mass of O2, and I will find that I have 0.125 moles of O2. Now then, and only then, can I use the stoichiometry to convert moles of O2 into moles of MgO. According to the balanced equation, every time 1 mole of O2 goes away, 2 moles of MgO show up. So there's a 2-to-1 ratio that I line up to eliminate the O2 and produce MgO. So it is lined up as you see in step 2. Notice the moles of O2 cancel, and my answer comes out in moles of MgO. So the dimensions line up correctly, so the numbers are lined up correctly. And I'm told to take 0.125 times 2, divide by 1, or reacting my 0.125 moles of O2 will produce a 1/4 mole of MgO. Now, how much does that MgO weigh is actually what question I'm asked. So I find the molar mass of MgO, and when I multiply by that molar mass, which is 40.3 gram per mole, times the 0.25 mole of Mg, I get that I'm going to produce 10.1 grams of MgO. Now, before we move on, here's another interesting point. I reacted 4 grams of O2, and I produced 10.1 grams of MgO. Guess where the additional mass of MgO came from? It didn't come out of thin air. It obviously came from the magnesium I reacted in addition to the oxygen. So if I formed 10.1 grams of MgO, and I used 4.0 grams of O2 in that process, then without question, 6.1 grams of Mg must have been used, because the mass of the product formed is formed only from the reaction of the Mg and the O. And nature works in such a way that that mass must be conserved. Now, I didn't do a stoichiometric calculation to show how much Mg would have been used, but if I did, it must be such that the sum of the product is the entirety of all Mg used and all O2 used, so it must mean that 6.1 grams of Mg must have been used. We'll explore that in some later calculations. Here I show the balanced equation for what I will call decomposing ammonia. Notice I have a balanced number of N's and H's on each side. So if I decompose 115 grams of ammonia, how many grams of H2 would I expect to produce by breaking down the 115 grams of ammonia? Okay, now you might think that I can directly convert using the stoichiometry of 3 to 2 from the balanced equation, the mass of ammonia into the mass of H2. But what I must more correctly do, since the stoichiometry describes the number of reacting and producing molecules, I must convert my mass of ammonia reacted into moles of ammonia reacted. So I take my 115 grams of ammonia, divide by its molar mass of 17.03 gram per mole, and note that I had 6 3/4 moles of ammonia to begin with. Now I can use the stoichiometry. There's a 3 to 2 ratio between the H2 and the NH3. I line it up to eliminate the NH3, and then dimensionally speaking, the numbers are lined up correctly to produce the moles of H2 reacted. And I will find that 10.1 moles of H2 react when are formed, when 6.75 moles of ammonia are reacted. So then I can take my moles of H2 and convert it into grams of H2. And I do so by multiplying the moles of H2 by its molar mass, and I find that 20.4 grams of H2 are produced upon decomposition of 115 grams of ammonia. Now there's another thing that must be true as well, and that's that 94.5 grams of N2 must be 94.6 grams of N2 must have been formed simultaneous to the 20.4 grams of H2 being formed. How do I know that? Well, the NH3 weighed out to be 115 grams, and when I decompose it, 20.4 of those decomposed grams are due to the H2 that was present in that NH3. Well, guess what? The rest of it must be due to the N2 in the NH3, and if I subtract 20.4 from 115, I would get 94.6 grams of N2 that must have been the remaining component of that ammonia. Now, I could have come to this same conclusion by taking the 115 grams of ammonia, converting it into 6.75 moles, as I did in step 1, but now use the ratio connecting NH3 to N2, and that would have been 1 mole N2 divided by 2 moles of NH3, then that would tell me the moles of N2 that I would have produced. Then I could use the molar mass of N2 to find the grams of N2 produced, and I bet you it would have been 94.6 grams, because that's the way nature works. Another example here, doing it with a single replacement reaction. I have in a reaction vessel 2.75 grams of copper 1 nitrate, and I wish to know how many grams of zinc are required to perform this single replacement. If I use 2.75 grams of copper nitrate, first I must use the stoichiometry to find information out about the zinc compared to the copper nitrate, but I can't do that directly from the mass. I, in step 1, convert the mass of copper nitrate into moles. Then I use the stoichiometry of 2 to 1 to find the number of moles of copper, of zinc that is required to react with that copper nitrate. Then I can find the mass of zinc I would need to weigh out by changing the moles of zinc into grams of zinc, and I find that I need 16 grams of zinc to react completely with my 2.75 grams of copper nitrate. Another stoichiometry example problem. I'm not going to go through the gore and detail of this. However, I believe you should. Maybe you should get this slide, cover it up from the top, work through the problem, and make sure that you can calculate how many grams of sodium nitrate are produced when we completely react 1 gram of iron nitrate. You should work that out on your own just to make sure that you are able to do these kind of calculations. Here is yet another example of literally doing the same thing, just to give you a little more practice, because of course I'm going to be asking you to do this for me yourself. So maybe, again, rather than regurgitate the same information we've gone over on several other slides, I suggest you work through this yourself as a practice exercise.